Hello, welcome to ECEG 431. I realize I forgot to talk a bit about the Into Project 5, so I'd like to go ahead and do that today with you. So it's our second day of lecture. Kind of what I want to talk about is the computer that we've built using the hack chips. I'm going to talk a little bit about the memory map and the connection to hardware, how we load code onto our computer we built, the final implementation map, and then kind of just where we are going. So, as we have talked about, the hack computer is comprised of instruction memory, which accepts an address and outputs an instruction. The CPU, which we've talked about already, it outputs addresses and data and accepts data and instructions. And we have the data memory, which passes data and accepts instructions, and then peripherals, which are going to be connected to the memory map, which in our case is the screen and keyboard. That's the only peripherals. So if we look at data memory, we have one unified memory area. This accepts 15 bits of addressable space. We're talking about the data memory here. And so within this, from 0 to 16,384, that's 2 to the 14 bits, that is 16K of RAM registers. Above this, and that's address 16,384 to 24,575, those are connected to the screen. In other words, 8K of memory mapped directly to a screen for our case. And then an address 24,576, right at the top of memory, is one register, and that is connected to the keyboard. So we have 15 bits going in of address space. Part of that's RAM, part of that's the screen, and part of that's the keyboard. I want to be able to work with that. Why is it not going? So 16K of RAM, you built that in Project 3. That has been made. The next thing we want to talk about is going to be the screen. So, the screen. There we go. When we talk about the screen, you're talking about memory mapped I/O. And so this is an example that I'm showing you is an example of memory mapped I/O or input output. The CPU communicates with the rest of the system using the address bus and the data bus. We talked a little bit about those before. So if the value placed in the address bus is at specific ranges, then the address decoder will connect the data bus to other pieces of hardware. And so the key, when we're talking about this, the CPU is just interfacing with the address bus and the data bus as normal. The CPU really has no concept of what it's talking to. It just places values in the address bus. And it happens to be that through the address decoding, well, we are actually then connecting the data bus to some other piece of hardware. And in fact, that's exactly what we wanted to do here with the screen. So we'll not be dealing with the screen itself, or not making that, I guess. Instead, we're using a built-in screen chip. And its interface is that it has a 16-bit input named in for data, a 13-bit address input named address, a 1-bit input named load, and then a 16-bit output named out. And you'll see this is very similar to a RAM chip and how the interface is working, because essentially a screen, this interface we have, is basically a regular RAM chip that happens to have a display output side effect, which is what we want. So we write to this set of what looks like memory, just as if it was a RAM chip, and that is the same as writing to the screen. The internal driver would work with that. The other peripheral we have is the keyboard. It's the same idea as a screen. When we access that particular register, we are then now communicating with the keyboard. We can simply read from that register to see if there is a key pressed and what that key is. The keyboard module emits the scan code of the current key pressed, or to 0 when there is no key pressed. What are the scan codes, you might be asking? The scan codes that this keyboard generates are basically standard ASCII codes with a few other weird things in there, such as F1 and delete. But these are the scan codes. I think Bliss is showing the binary value. So whatever key it is, we can see the number. So for instance, a right bracket is decimal 91. We read that. Aha, the square bracket is being pressed. All right. Next, we're going to use the built-in keyboard and treat it like it's a read-only 16-bit register that happens to have this keyboard input side effect. So that should be pretty easy to work with. So this kind of gives us our memory map then. To make our RAM, our setup, we use the RAM 16K chip that we've built and the two built-in chips, screen and keyboard. And so the trick is going to be that you have to work on is decoding the address and routing the address input to the corresponding chips. In other words, You just need to write the decoder piece, kind of sits here between the address and input that connects to the RAM screen or keyboard. And once you have that kind of done, then this just looks pretty much like a giant RAM chip, and in fact, that's what it is. The decoder just connects to different hardware. So that's memory mapped I/O. Next is the instruction memory, and this holds the actual instructions that we want to then run. And so the idea here is that we have some piece of program, hack code, that gets put into instruction memory, and you will then load that instruction memory and start running that on the computer. And the way that works is that we assume that the program is loaded onto instruction memory, that's happening externally somehow for us. In the CPU, the reset button would get pressed, and then the program just takes off and starts running. So for us, the hardware simulation is how it's getting these hack programs onto the instruction memory is just using text files with a load program service that happens externally. We can think of this as like we are burning a chip with instructions at the factory or somewhere else, and then we put that onto our code and it runs. So the instruction memory is a hack instruction memory. The hack instruction memory is made using the built-in, so you can go ahead and use this ROM 32K chip. So that tells you that that's the limit of the instructions that we can use, but this chip functions like a 32K RAM chip, or random access memory, but it is ROM and read-only, and it just enables you to load then programs onto it. Hard to see this on the screen, but it says that we have a 15-bit address going in to the ROM 32K chip and a 16-bit data value going out. And so we're really taking the CPU's output, the address we want to access, and we are simply passing that instruction off to then the rest of the computer. So building out the hack. So you have all the pieces now. We have the CPU, we have the RAM, we kind of build that out into the computer. Starting with, to build a computer, we start with the CPU, and that's going to have the basic piece. So we know we have an external reset input that's going to connect to the CPU, and we have various other connections. So we have the ROM, the 32K of read-only memory, which has our instructions. That instruction piece, the actual what we want to run, is going to be connected there to the CPU. Okay, that's easy enough. Well, the CPU is going to need to read and write from memory. So we're going to take the memory chip, put that over here, and then we need to figure out how we can connect everything. But we do know that the output from memory is going to go and feed back and come into the CPU as input from memory. If we want to write to memory, well, then we need to connect that up to memory chip. The data we want to write out to memory, alt-m, is going to connect to the memory chip, and of course then the address we are writing to. Wire that up. Great. That sounds good. The CPU and the RAM data memory is working. Next, we just need to take the program counter output of the CPU, wire that back into the ROM 32K so it knows what address to read if we want to jump, increment, whatever. And there we go. That is a full computer. The instruction memory, the CPU, and then the data memory. It's all wired up. Add in our screen and our keyboard. We can have some external inputs, and we are completed. We have built a computer. So that's kind of a big deal. So where have we been in the course so far? In just a few weeks, really, we have built everything we need to make a functioning computer. This computer we have is infinitely tweakable. And like all computers, they are designed to run store programs, and those programs can do infinitely variable tasks, even though we've made these with a fixed set of hardware. And that's what's kind of cool. At this point, you now have the skill to design your own computer. And that should be pretty empowering. These are not difficult machines to make. In fact, they're pretty simple. They're just a bunch of chips we have together, we load programs on, and now we can change the world. Computers are everywhere. They're getting more and more places, especially if we electrify things like car and just have tons and tons of mini computers all over the place. And those choices in how we use those computers, where they show up, the algorithms they are running are affecting all of modern life and our built world. So this is a pretty big piece of power, really, that you have in how we use computers. It doesn't have to be a big desktop computer. You make a very tiny piece of computer somewhere that's running off in a specialized application. And that's really what we're seeing in the embedded world. So we start with these elementary logic gates at the bottom. And from those, we were able to make things like an adder, the program counter, the ALU, the CPU. We did have to include a flip-flop, and then that lets us make things like registers, and then we can store data. All this is connected. We have registers, RAM, and memory, which we get up to having the CPU and memory. Those come together to make our computer. So here it is. Here is the abstraction for our project. We have the hack computer with 3 external pieces. The only input is the reset button, or the reset input. We also have the screen and then the keyboard. Inside that, we have ROM, the instruction memory, the random access memory or data memory, and of course the CPU. Diving in on the CPU, well, here we have that, and inside of that is what you have been working on, wiring up all the control bits that we can decode the instruction, tell the ALU what to do, and then feed our inputs and outputs to the appropriate spot. A big tip on this, use HDL subscripting to really help you parsing out and routing that instruction, otherwise it's going to be impossible. Because those different pieces of the instruction are going to tell different muxes and different pieces where to route our data. You made the CPU implementation. Here's the stub, I guess, the skeleton file of what the CPU is going to look like as you wire that up. And each of those HDL files, just like with the computer, you use to make all the other pieces for this project. So for this one, the RAM 16K is built in Project 3 to make our RAM chip. RAM 16K was built. The screen and the keyboard are also built in. Take all those together, wire those up. That's going to be your memory. And the last part is just to make the computer. This is it. This is the stub file for the Computer.hdl. It has one single input. Load your ROM, load your CPU, load your memory. That's going to be everything. And with that, that's it. You've gone through. You have made a computer. We're going to start shifting now more into the software side of the course. I hope you have seen areas in this computer we've made for where you may want to optimize things, because there's a lot of room for that. But the idea stands. That is a computer. You've made one. You have the power to do it. It's kind of cool. So with that, happy coding for Project 5. Let me know how I can help, and good luck.